Okay, guys, I don't know. I messed with the mic a little bit. Is it working now? Can you guys hear me? Someone type in the chat. Yes, okay, wonderful. Thank you. I don't know what the deal is. I haven't changed anything, so I'm not sure why it wouldn't work initially, but that's okay. As long as it's working now, we should be good. Okay, so let's get going. So last time we were talking about acids and bases, just general stuff. And so now we're going to talk about or finish up kind of the general stuff. So talk a little bit about polyprotic acids, then we'll go into the quantification of kind of acid-base strength. And then our last topic will be buffers. And so that's the end of this chapter, which then leads us into your exam for Thursday. And so you've got an exam on Thursday, and then next week we will talk briefly about our final kind of two topics, and then you've got a final exam. So there's not much left, guys. So let's talk about polyprotic acids. So we talked in general about acids, and the acids are things that donate protons, or meaning that they ionize in water and they give H+. So H+ and proton, we interchange those terms. So some substances for each individual one that you put in solution, you get one proton, okay? But there's other substances that for each individual molecule that's in solution, it can give up more than one proton. So those things would be polyprotic acids. So some good examples are carbonic acid and phosphoric acid. So carbonic acid, H2CO3, for each one of those that goes into solution, it has the potential to give up 2 H+, okay? And phosphoric acid, H3PO4, could give up 3 H+. Now, initially, these things, when they go in solution, the first proton comes off, and depending on kind of the environment will determine whether or how much of a second one or even a third one will come off of a given molecule, okay? And so it kind of depends on the conditions. So they can, give up kind of what is needed in that solution. Okay, so when we deal with these polyprotic acids, we can write the equilibrium associated with their ionization in water, just like we can with any kind of weak acid. So let me go back before I put up this polyprotic one. If we think about a monoprotic acid, something like HF, okay, so if we have HF, that's a monoprotic acid. And when we put HF into water, it goes into solution, so it dissolves, and it interacts with water by ionizing. So remember, we could write that down as an equilibrium reaction, and what you would get as a product would be F-, and so that's the conjugate base of our acid, hydrofluoric acid, okay? And then the proton, the H+ that comes off, would attach to the water molecule, forming the hydronium ion, okay? And so that type of equilibrium exists for any kind of acid in solution, okay? If it's monoprotic, you just have kind of one step of that occurring, okay? But if it's polyprotic, then it happens in multiple steps. So you actually have multiple equilibriums associated with it. So if we want to look at it kind of in a generic form, we could say, okay, we have some polyprotic acid that is H3A. And so this is my polyprotic acid here. It's triprotic. Specifically, it can give up 3 protons. And so if I put that in water, initially what happens is it loses 1 proton. Okay, so it loses 1 proton, making H2A-. Okay, and then the hydronium ion, because the water molecule picks up that proton. So in that first reaction, the H3A is my acid, okay? And then the H2A minus, that's my conjugate base of that reaction, okay? And so it now has one less proton, but that H2A minus still has protons it could potentially give up. And so what happens is that could further react with water. So the H2A minus could then react with another water molecule, and it can give up a second proton, then forming the Ha2 minus. And so it lost an H plus, so now it has a 2 minus charge instead of a 1 minus, and it has another negative charge on it, okay? And so in that particular reaction, the H2A minus is behaving as an acid, okay, and forming a new conjugate base, okay? And then you can look at that third one, and basically it's the same type of thing. That conjugate base that now has been formed, that still has a proton that it can give up. And so that Ha2 minus can then interact with a new water molecule, then forming A3 minus, so losing that third proton, okay? And so in this step, you have the Ha2 minus is behaving as an acid, and it's forming its conjugate base of A3 minus, okay? And in all three of those reactions, water is acting as a base, okay? Because the water molecule is picking up that proton, and the hydronium ion in those three are actually your conjugate acids in the particular reaction. So these are actually our base in all of those reactions. And these H3O pluses, those are our conjugate acids, okay? And so those are all Bronsted-Lowry kind of acid-base reactions. And so you have a reaction with water, and it's actually an equilibrium. And so it has an equilibrium constant associated with it. So what I have over on the right, Ka1, Ka2, and Ka3, because just like this reaction up here, that monoprotic acid, that has a Ka associated with it. That Ka, remember, you can write an equation, the product concentrations over the reactant concentrations, okay, would be the expression that is related to that. And so you could write that. You could do the same for these three reactions, but they all have their own Ka value, okay? So we wouldn't just call them Ka, we say Ka1, so that's the first ionization step. And Ka2, that's the second ionization step. And Ka3 would be the third ionization step for that particular acid. Now, those reactions that I have on this slide are in the generic form. So it's just some generic weak acid, some generic triprotic weak acid. Okay, so those are the types of reactions that you would see for like H3PO4. If we wrote the reactions, the first step, you would have H3PO4, and that would be in solution, and that would react with H2O liquid, and that would reach an equilibrium where it gives up a proton, okay? So it ionizes, and it would form H2PO4 with a negative charge because it loses an H plus, okay? And then that H plus attaches to the water molecule, so it forms the H3O plus, okay? So this would be the first step for H3PO4's ionization in water. And so that would have a Ka1 associated with it. And that Ka1, you can write an equation for taking the products of that reaction and putting it over the reactants. But remember, we drop water out of that equation because it's a pure liquid, okay? And liquids and solids, we don't put those equations, okay? Now, for the carbonic acid, I actually have the reactions here at the bottom of the slide, okay? So for the carbonic acid, the H2CO3, that donates 2 protons. And so it can go through 2 steps of ionization. And so the H2CO3 can lose 1 proton, forming HCO3 minus, and that has a Ka1 associated with it. And then the HCO3 minus can then ionize again, forming CO3 2 minus, having a Ka2 associated with that step. Okay. So however many ionizable protons, so how many H pluses something can give up, will relate to how many Ka values are associated with that substance. Another thing to realize is these Ka values, they're just an equilibrium constant. So they are a numeric value, and those are typically tabulated values you can go look up. Okay, and you can utilize them then to relate to the concentrations of the substances. We won't go that far, but it's good for you to realize that these are all values associated with some sort of weak acid, okay? And a weak acid does not ionize very much, okay? So the majority of a weak acid in solution is the substance still put together. Okay, so there's not a lot of H plus produced, and there's not a lot of its conjugate base in solution. So that ratio of the products to reactants is going to be a very small value. Okay, so your Ka values are always very small. And if you're looking at a polyprotic acid where it ionizes in steps, those values are actually going to get smaller as each step goes on. Because in order for the second step to occur, the first one has to, right? And if the first one doesn't occur very much, then the second one is going to occur even less. And really it's because you already have, you know, in the second step or even in the third step, you have something negative to start with. And if it already has a negative charge, it's going to be less likely to give up some more positive, okay? So those Ka values actually get smaller and smaller and smaller as there are more steps in that process, okay? So all of them are small no matter what. But if it is a multi-step process, the values will get smaller. So as you can see for the carbonic acid, the Ka1 and Ka2, the first one is on the order of 10 to the negative 7th, which is a pretty small value. But the second one's even smaller, being on the order of 10 to the negative 11th, okay? So that's as far as we'll go with polyprotic acids. You should just realize, what does it mean if it's a polyprotic acid? It can give up more than 1 proton, and kind of the steps it goes through, you should understand that it gives up 1 proton at a time, and each of those is related to a numerical equilibrium constant. Okay, and so we can use that to quantify things about a solution that contains an acid, okay, whether we're talking about a monoprotic acid or a polyprotic acid, okay? So this is just kind of an extension of what we were already talking about on, Thursday last week. Okay, so let's go into the actual quantification, how this stuff can help us quantify information about acid strength and base strength of our particular solutions, okay? And so there's one other kind of piece of information you need to know to be able to do these quantifications. You need to understand that water actually, even on its own, will ionize, okay? So we already know that water is an amphoteric substance. It can act as an acid or a base because we've looked at reactions where water is either donating a proton, so giving up H plus, and at reactions where water is picking up a proton, okay? And so it can do both, and it doesn't actually have to be in solution with some acid or base to do that. Okay, now if water is in solution with an acid, it's going to naturally pick up the H plus from the acid, so it's going to be acting as a base in that case. If it's in solution with a base, it's actually going to give up a proton, acting as an acid, you know, to react with that base. But if water is just by itself, it will interact with itself. Okay, so it will go through a process called autoionization. Okay, and so that's what this reaction that's given is. It's representing the autoionization of water. And so you have two water molecules, okay, and they can come together and interact, one of them acting as an acid and one of them acting as a base. And so the one acting as an acid would give a proton to the one that is acting as a base, okay? And so then what you form is the hydronium ion, H3O plus, and the hydroxide ion, OH minus, okay? And so this is something that naturally happens just in water or actually in any aqueous solution, okay? So if there's water around, then this is always happening, okay? So it can be happening right alongside with these other ionizations that occur, okay? So it always has the potential to interact with itself. Now, how much it happens depends on, is it just pure water, or is there also some acid or base present, okay? And so we can quantify kind of how much autoionization is happening with that water by looking at the autoionization constant. So the constant associated with this equilibrium, okay? And so we label it as KW because it's the K for water autoionizing. Sorry, guys. So this autoionization reaction, then that K value is going to be equal to the product of the hydronium ion concentration and the hydroxide ion concentration. Okay, so it's not over anything. You could say it's over 1 if you want, because the H2O liquids you don't put in that equation. Okay, but the nice thing about this equilibrium is that even if there is some additional acid or base added to that water, this equilibrium has to hold true. And so if you add some extra H3O plus, then the equilibrium will shift to the left based on Le Chatelier's principle. So it will try to consume that added substance, but that product of those concentrations will still remain constant, okay? So this equation, this KW equals H3O plus times OH minus, we can use that for any aqueous solution, whether it's pure water or it's some acid in water or it's some base in water or some salt in water. This equation always holds true, okay? And we do know the value of the KW. But you have to be careful. It is actually a temperature dependent value, just like any other K. So we will look at, the most useful case. We'll look at 25 degrees C because that's pretty much room temperature. And normally what we're working with are things at room temperature, okay? If you're working at some temperature that is much higher or lower than that, you have to be careful because this value will be quite a bit off. Okay, but you guys should assume that we're at 25 degrees C and that you can use KW equals 10 to the negative 14th, unless if you're told otherwise, okay? And so the KW of water is 10 to the negative 14th, meaning the product of your hydronium ion concentration and your hydroxide ion concentration is equal to 10 to the negative 14th, always, okay? And that's whether or not it's just water or you have other stuff present, okay? Now, if it is just water, then the only place H3O plus and OH minus are coming from is from this autoionization process. And if that's the case, that H3O plus and OH minus must be equal. So I guess I kind of shorthanded it on the second part. This H plus, remember, sometimes we'll write it as H plus, sometimes we'll write it as H3O plus. I don't do that to confuse you. That's just, people interchange them a lot and don't even really realize they're doing it. So the H3O plus and the OH minus need to be equal, okay? If you're in just water. So that's true if you're in pure water. If there's anything else present, those two aren't going to be equal. Okay, but if we're really just talking about water, they're equal. So if they're equal, you could take the square root of that KW because that would tell you what each of those would be. because essentially it's like they're both equal to x, and so you have x squared. And so you could take the square root of the Kw, and it tells you. So in pure water, okay, this value is the concentration of your OH minus and your hydronium ion concentration, okay? And so this is in pure water. So you have to be careful that this is only true in pure water. If you have acid or base present, it's going to alter those concentrations. So one of them is going to be higher than that. One of them is going to be lower than that if you're not in pure water, okay? Or if you were at some other temperature that's quite a bit away from room temp, then it's not. Okay, so we can utilize this to actually quantify hydronium ion concentration or hydroxide ion concentration actually in any solution. Okay, so if it's pure water, we know it's 10 to the negative 7th mole. Okay, but any other solution, you can use this equation. Okay, so anything in water, whether it's pure water or if you're talking about some acid or base solution, if you know one of those two things, you can solve for the other, okay? So if you know the H3O plus concentration in this acid solution, you could plug it into this equation and calculate how much hydroxide ion there is, okay? Because those values are going to have to equal that Kw of water, because water will either ionize more or go back to the neutral form to keep those balanced, okay? Now, more commonly, what we talk about when we're talking about acids and bases and kind of quantifying their strength is pH and POH. So pH is the most common, so we look at that first. So pH really is a measure of the acid strength, okay? And the lower the value is, the stronger the acid, okay? And so really pH is less than 7 are acidic solutions. A pH equal to 7 would be neutral. A pH greater than 7 would be a basic solution, okay? So high pHs are basic, low pHs are acidic, okay? And that's on the scale of about 0 to 14, okay? Really, your pH values could go a little bit negative sometimes, and they can go over 14. So that's why I say about 0 to 14 is your pH scale, okay? And really what pH is it's kind of a measure of your hydronium ion concentration. It's a measure of it on a log scale, okay? So how you calculate a pH is you need to know the hydronium ion concentration. So how much essentially of your acid is ionizing, because that's going to determine how much hydronium ion you have. And so once you know that concentration, so it's got to be in molarity. That's why we have that in square brackets in that equation. And you would take the log of it, and then you change the sign. So the negative log of the hydronium ion concentration is what the pH is, okay? And you can actually, if you already know the pH of the solution, you can back calculate the hydronium ion concentration. So this is another thing that we only need to actually know one, okay? So if you know hydronium ion concentration, you can get pH. If you know pH, you can get hydronium ion concentration. So you usually have one or the other, and you can calculate whatever you don't know, okay? And so if you have a stronger acid, that's something that ionizes more, okay? So it creates more H3O plus, okay? So that H3O plus concentration goes up and your pH goes down, okay? Whereas if you have a weaker acid, less of it ionizes, meaning there's less H3O plus in solution, so your pH is actually going to end up being higher, okay? Whereas we could talk about this kind of from a perspective of a base. And so we could talk about it on the scale of POH. And so that's really considered to be a measure of base strength. Now you could measure the strength of a base based on the pH scale It's just high values then would be a strong base, as opposed to low values are a strong acid. Okay, so it's just opposite end of the scale. So your pOH scale kind of flip-flops. Okay, so on a pOH scale, low values again are indicating a strong thing. Okay, so low pH is a strong acid, low pOH is a strong base. Okay, whereas a high pOH would then be a weaker base, or, if it's above 7, it's acidic. Okay, so it's just a reversal. It's looking at it from a different perspective. We don't use pOH very often, but it is good for you to realize that we could quantify it that way. And so if someone does want to quantify it that way, you should be familiar with what it is. Okay, and so instead of quantifying, the amount of hydronium ion, it's actually quantifying this based on the hydroxide ion concentration. Okay, so a pOH is the negative log of the hydroxide ion concentration. Okay, whereas you can also, just like pH, you can use to quantify hydronium ion concentration by doing 10 to the negative pH. You can do the same with hydroxide ion. You can calculate the hydroxide ion by taking 10 to the negative pOH. Okay, so the main equations I give there kind of in red, this is the most important one for this, okay, is quantifying pH in terms of hydronium ion concentration. This one here that I have to the right in gray, that's just rearranging that equation. It's the same equation, okay? So you're doing the inverse log, to get rid of that log. So 10 to a log is going to cancel it out. So you do that on both sides of the equation, and you come up with this other version, okay, that's pre-rearranged for you, basically. Okay, and you have the similar equations for the pOH scale. And so if you have a stronger acid, remember, it ionizes more, gives you more hydronium, a lower pH. If you have a stronger base, you also get more ionization, but in that case, you would get more OH minus, thus a lower pOH. Okay. Now these two things are tied together. So this is why sometimes people will use the pH and pOH scale, is because they're directly related to one another. The sum of pH and pOH is always 14, at least at room temperature. Again, so 10 to the negative 14th relating your hydronium and hydroxide, that's true at room temp or at 25 degrees C. pH plus pOH equals 14 also if we're at room temp, okay? So really, once you know one of those things, you can get the other three, really. And so let's look at that kind of summarized, some kind of summary information about all of this stuff. Your book gives you lots of nice, tables and diagrams to try to tie all this together for you, but let's talk about it. So in table 13.7, they talk about kind of the difference between different types of solutions. So we can have a solution that's considered neutral. We can have acidic solutions and basic solutions, okay? In a neutral solution, you have equal concentrations of hydronium ion and hydroxide ion, okay? So they're going to be equal. If we're at room temp, 25 degrees C, that's 10 to the negative 7th molar, or 1 times 10 to the negative 7th, same thing, okay? And so they're both equal to that. And the kW of water is 10 to the negative 14th, okay? So this table of information that they're talking about, this is at 25 degrees C. So again, just remember, if you are trying to work with pH and hydronium and hydroxide ion concentrations at some other temperature, if it's pretty far off from there, you can't assume these things are true. You have to be careful. You would have to re-quantify it. And then if it's acidic, what you have to realize is instead of the hydronium and the hydroxide ion concentrations being equal, now you have more H3O plus, okay? So something has added in extra H3O plus, making it to where now the ratio of those things isn't the same. They're different values, okay? So you're going to have more than 10 to the negative 7th molar of hydronium ion concentration in an acidic solution and less than 10 to the negative 7th of your hydroxide in an acidic solution. Okay, but the Kw of water still holds true. So the product of whatever that greater than 10 to the negative 7th value is and less than 10 to the negative 7th value is still going to come out to 10 to the negative 14th. Okay, whereas in a basic solution, it's going to be completely opposite. There's more hydroxide, less hydronium. Okay, but the product of the two will still be that constant. Okay, so the diagram kind of on the right, that gives you, you know, kind of at different pH points, what all the other stuff would be. So at pH of 14, that's when you have 10 to the negative 14th of hydronium ion, and you have nearly zero, or sorry, your POH is 0, and your hydroxide is around 1. Okay, and so that's a very basic solution. You have a lot of hydroxide and not very much hydronium. Okay, whereas at the other end of the scale, if you had a pH of 0, you have about a 1 molar solution of hydronium, but you only have about 10 to the negative 14th molar of hydroxide. Okay, and notice that the pH and POH scales are reversed. Okay, so if you have a pH of 14, you have a POH of 0, or a pH of 13, you have a POH of 1. So those always sum to 14. Again, as long as we're under kind of normal conditions. Okay. Okay, now looking at how you calculate all of this stuff, there's kind of 4 different equations. Okay, and so there's an equation to convert between hydronium and hydroxide. And that's the Kw equation. Okay, so that's what's at the top of this. Okay, so the product of your hydronium and hydroxide has to be equal to 10 to the negative 14th. That will get you a conversion between hydronium and hydroxide. So if you know one or the other, then you can calculate the other. Okay, so you only need to know either hydronium or hydroxide, and you can calculate the other one. Okay. Same with pH and POH. So those are tied together. So the sum of pH and POH always has to be 14 as long as we're under standard conditions. Okay, meaning if you know the pH, you can calculate POH, or if you know POH, you can calculate pH. Okay, so you can always calculate those from one another. And then there's also conversions between pH and H3O plus, right? So you can quantify it based on this negative log equation, right? You can convert between the pH and H3O plus. Now they rewrite that equation in the other form. So it looks like, this kind of looks like 2 equations, but this is just the same equation rearranged. Okay, so it's one relationship. They just rearrange it because a lot of times people forget how to get rid of a log. Okay, but the key there is if you know hydronium, you can get pH, or if you know pH, you can get the hydronium ion concentration. And same with the OH minus. You have a similar equation for the hydroxide, right? So the negative log of hydroxide gives you POH, or 10 to the negative POH gives you hydroxide ion concentration. Okay, so really, you see how this is all tied together? What you should realize is you actually only need one of those 4 things. So there's 4 quantifications, there's 4 ways we can quantify information about acid or base strength. We can quantify it in terms of how much hydroxide ion is in solution. How much hydroxide, how much hydronium ion is in solution. So either of those, or based on a pH or POH. Okay, so all 4 of those things actually are communicating acid or base strength to you, just in different kind of units, I guess you could say. Even though, please realize, a pH and a POH are unitless values. It's one of the few times in this class where you can report a number and it has no units, okay? Whereas the hydroxide and hydronium ion concentrations are in molarity, okay? So you put a capital M with them. But really realize with this, you only need one of the four. Once you have one of those, you can calculate the other three from it always by just kind of following this box. Okay, so you start somewhere and you can just follow those arrows and convert all of these other things. Okay, so you do need to be able to convert between these and utilize whatever of the four pieces of information you're given, okay, to quantify any of the others. So let's go through, or I guess before we go through examples, I did want to mention something about sig figs because things are quite a bit different for this than our typical calculations. So a logarithm is really an exponent, okay? And the rules for sig figs with exponents, when you raise something to a power, is quite a bit different than multiplication, division, and addition, subtraction. So really, there's a new set of rules. Now, don't stress about this too much. I will try to point out to you, at least on the exam, say, give me this many sig figs. You know, or this many decimal places. You don't have to stress about it too much, but it is good for you to realize there's another set of rules. If nothing else, you can go look it up if you need to. But basically what it is when you take the log of something, or the logarithm, okay, that's what it is a logarithm of some value, the result should be reported to the same number of decimals as the starting number of sig figs. So this is really obscure compared to the rest of them. Okay, so it seems very odd that we're linking number of sig figs to now decimals. Okay, so if I take the log of, for example, 22.5, if you punch that in your calculator, you do 22.5 and hit the log button. Or if you're using kind of a graphing calculator, you hit log and in parentheses, you put 22.5, just like this. It should give you something, which actually I wrote the result out. Let me see if it should give us more than that. So it gives you something like 1.352182518. So it gives you a bunch of numbers, okay? But I reported the answer as 1.352, okay? And that's because the number I took a log of has 3 sig figs, right? The 2, and the 5. It's 3 sig figs. So I need to report 3 decimals, okay? So like when you're using logs, you're calculating, say, a pH or a POH, okay? So however many significant figures you have for the concentration, that's how many decimals your pH should have, or how many your POH should have. Meaning you should never give a pH that has no decimals. Because if you report a pH with no decimals, it means that you had no significant figures in your log, which is never going to be the case, okay? The reverse would be true if you do what's called the anti-log. So you do the inverse of the log. And so that's the 10 to the value, okay? So if we do the anti-log, or 10 to the, say, 2.345 is what the example I have there for you. On this one, I actually did type out what the calculator gives you. So it gives you 221.309.471. Okay, and you wouldn't report all of that. You would focus on what you took the anti-log of had 3 decimals, so you need to report 3 sig figs. Okay. Now, like I said, don't get overly stressed about this. Realize that there is a rule, and so it can cause things to seem to gain or lose sig figs when you do logs or anti-logs. So it's good for you to be aware that there is kind of a set of rules. You can look it up. I'll try to point out to you guys on the exams, but you should at least realize it doesn't follow the same rules as multiplication, division, or addition, subtraction. It's all linked to sig figs. The anti-log is the 10 to the negative. So it's really called the, or sorry, not 10 to the negative, it's the 10. So for instance, this log of 22.5, right, that gives you the 1.352. If you wanted to do the anti-log is 10 to the 1.352, okay? And so on your calculator, usually there's a 10 to the X button, okay? So either there's a 10 to the X button, some calculators might have it labeled as anti-log. Or you just type 10 and then hit either the caret button on your calculator or the Y to the X and then type in that value that you want to do the anti-log. Okay, and so same with this example down here where I wrote anti-log. Sorry, I probably should have just wrote it as 10 to the 2.345. And so that should give you, and so if I type in even just manually 10 to the 2.345, that gives me the 221. Okay, so depending on what calculator you're looking at, sometimes they'll write them differently. And so that's why on the pH equations, they did actually write it as 10 to the value. And the reason in the pH where that negative comes from is because the pH is the negative log. And so we have to move the negative over when we're back calculating the hydronium. Okay, and so this equation like pH equals negative log of H3O plus, when we rearrange that, basically you can divide by -1, right? And so that would tell you negative pH equals log of H3O plus, right? And if we need to get rid of that log, we're going to do what's called an anti-log, which is really just doing 10 raised to this stuff. So 10 to the negative pH and 10 to this. And so the 10 to the log cancels and it becomes H3O plus is equal to 10 to the negative log. So that's what that is. Raising something, or doing 10 to that substance or value, is the anti-log. Okay, guys. And so usually it's, if you have a log button on your calculator, if you go to the second function, then it's the alternate option for that same button normally on most calculators. But I've got lots of examples. Let's go through some examples, and you should try to punch them in your calculator and make sure that you can get these values. Because if you can't punch it in your calculator to get it, you're not going to be able to answer questions on quizzes and tests and homework and all of that. Okay, so let's see. Let's start with one. We've got, hold on. Sorry, guys. This thing is, get this thing to disappear. There we go. Maybe. What are the H plus concentration and hydroxide ion concentration in household ammonia? And I tell you an aqueous solution, that's an aqueous solution that has a pH of 11.70. So when I say household ammonia, that's what I mean, an aqueous solution with a pH of 8 or 11.70. And so it has NH3 in it, and that's the resulting pH. And again, this H plus, that's kind of our lazier way of writing. That's the same thing as H3O plus, okay? So sometimes we'll just simply write H plus, same thing, okay? So I want to know H3O plus, and I want to know OH minus, and my solution has a pH of 11.70. So I have pH, I should be able to quantify each of those from that, okay? And so first off, you have your equation pH equals negative log of H3O plus, right? And the rearrangement of that equation is that H3O plus equals 10 to the negative pH. So you just need to plug that in. So your H3O plus is going to be equal to 10 to the negative 11.70. So we would actually type that in the calculator. Okay, so you can do 10 to the negative 11.0. Whether you use the actual anti-log button on your calculator or you manually type in, 10 to the negative 11.7, you should get, oh, whoops, I just cleared that. Negative 11.7, 10 to that. And so we get, let's see, And for this, we're doing an anti-log. So really, if we try to follow sig figs, guys, you should always focus on the decimals of the pH. So it has 2 decimals. So my answer should have 2 sig figs. So that's going to come out to 2.0 times 10 to the negative 12. And that should have units of molarity, okay? Because it's a concentration we're looking for. Okay, so that should be my answer for that, okay? Now, we want the hydroxide concentration, and we know the hydronium now, so I can use that, okay? So remember that the Kw of water equals your H3O plus times hydroxide, right? That equals the Kw, which is 10 to the negative 14th, okay? Or you can write it as 1 times 10 to the negative 14th if you'd prefer. Same thing. So I can use that equation with the information that I already have now. Okay, so I can just plug that in and take the 2.0 times 10 to the negative 12th. Okay, and that times the OH minus. Okay, now I dropped the unit there because the units are always funky in these equations because molarities disappear and reappear. So I'm just going to leave it off and we'll tack on the correct unit at the end. Okay, so that has to be equal to that. So that means OH minus must be equal to 10 to the negative 14th divided by the 2.0 times 10 to the negative 12. Okay, and so if you type that in your calculator, 10 to the negative 14th divided by 2 times 10 to the negative 12th, let's see, it looks like we get, and again, let's sig figs, you have 10 to the negative 14th is exact, so that's infinite sig figs, whereas this one has 2, so I'm going to round my answer to 2, so I get 0.0050 molar, okay? And so that is my other answer. That's my hydroxide, and this is my hydronium, okay? Hydroxide and my hydronium concentration. Okay, guys? So really it's just, you've got to pull the right equation. And if it helps you, go back to that slide that had kind of that box with the equations and think about what do you have. And so you'd start at the pH, which I can go back to that real quick. So for this problem, we knew the pH and we were looking for this and this, okay? And so first what I did is I took that pH and I used that equation to go to the hydronium. And once I had the hydronium, I used this equation to go to the hydroxide. Okay, so you just kind of follow the paths around that box to get what you want. Okay, so that's those answers. Okay, now let's look at another one. So now I say, what is the pH of a 0.020 molar aqueous solution of HBr? Okay, now I give you in this, or I want to know pH, and I tell you the concentration of HBr, okay? So now you have to be careful. I didn't directly give you hydronium, right? Or it doesn't look like it. So what you need to realize is HBr is a strong acid, right? And a strong acid, when we put it in solution, it ionizes completely. So really, when we have HBr, when we add that to water, it doesn't cause some equilibrium. It completely breaks up and forms H3O plus and Br minus, okay? And this is all 1-to-1. So for every 1 HBr, it interacts with 1 water molecule and gives you 1 H3O plus and 1 Br minus. So really, if we started with 0.20 molar, what you're going to get is 0.020 molar of H3O plus, okay? Because for every 1 mole of HBr, you would get 1 mole of H3O plus, and it's still all in the same solution, okay? So we did kind of directly give you, or indirectly, I should say, we kind of indirectly gave you the H3O plus by telling you the concentration of a strong acid. So I can take that now and I can calculate pH by doing the negative log of my H3O plus, which in this case is the negative log of 0.020. And again, I'm just going to go ahead and drop the unit because the unit disappears when we report the pH. Okay, so we take 0.02 and take the log of it and change the sign of that answer. And for this, if we look at sig figs, this has 2 sig figs in the concentration, so my pH should have 2 decimals. And so it looks like if we round it to 2 decimals, we get 1.70. Okay. And so let's see. How do you know whether to do the log or the anti-log? Well, in this case, the equation says to do the log, right? The anti-log is just, if in the equation, the way that we write anti-log is when we write 10 to the negative pH. That's the anti-log, okay? So sorry, on my sig fig slide, I wrote anti-log instead of 10 to this. That just is the typical way that is communicated. That's how you say that in words. So if we write 10 to the negative in the equation, you type in the calculator 10 to the negative. But in the equation, it just says log. So you use the log button, okay? And so that is just straight out what the equation is directing you to. And so you would use this if you were trying to solve for H3O plus, but you're not trying to solve for H3O plus. You already know H3O plus, right? Now we can plug back in. We can take this 1.70 and plug it in here, and it should give us right back that concentration, okay? Now, since it's rounded, it may come off a little bit off from there, okay? But if the equation has a log, it really means the log, not anti, okay? So you just need to use the right equation. You've got to pay attention to what do you have. So if we go back to that picture, in this one, here I can erase all of this junk, okay? So in this particular problem, you were basically given H3O plus, and you want the pH, right? And so if you have that and you want the pH, then it would be easiest to use the equation that's already solved for pH, right? This is solved for pH, so just plug in negative log of H3O plus, okay? So they kind of pre-rearrange those to try to help you, okay? Because we know most of the time we're not doing calculations with logs. And so if you can't remember how to get rid of a log, they're just showing you how directly. Okay, so let's go to another one. Now, what if I want the pH of a 0.040 molar solution of KOH? Okay, so for this, I want the pH, right? That's what I'm looking for. And I tell you the concentration of KOH. So I tell you it's 0.040 molar. Okay, and let's see. So for this, really you need to realize that KOH is a strong base. Okay, that you have to know. So you have to know when I put KOH in solution, really what I get is K plus and OH minus. There is no KOH anymore. Once I put that into water, what I get is K plus and OH minus. And since it completely breaks apart, that means if I had 0.040 molar of that, then I have 0.040 molar of OH minus, okay? And so that means I know my OH minus concentration, and so I can do a couple things with that. It's up to you. You've got two equations, so you can calculate POH. Okay, so you have an equation that says POH equals the negative log of OH minus, okay? or you have an equation that says, let's see, sorry, that H3O plus times OH minus equals 10 to the negative 14th, okay? And we have OH minus, so we can calculate POH or we can calculate H3O plus. Either way will help you get to the pH. I would use this equation and say that POH equals negative log of 0.40 molar. Okay, oh, whoops, I lost a 0. There we go. That's important. You can't drop that 0. Okay, and again, you can drop that unit if you want because it's going to disappear. And so you have 0.04, you take the log and the negative of that. And so that gives us a POH of 1.40, right? Because we have 2 sig figs, and so I'm going to do 2 decimals, okay? Whereas if I use this other equation, it would tell me OH minus must be equal, oh, not OH minus. I can solve for H3O plus. Sorry, guys. Erase that. So I can solve for H3O plus. That would be equal to 10 to the negative 14th divided by, 0.040. Okay. And so that's my hydroxide, and that gives me my hydronium. So 10 to the negative 14th divided by 0.040, and that should give you 2.5 times 10 to the negative 13th molar. Okay. So neither one of those is what we're looking for, right, in the end, but both of those can help us get there because I can take the POH and I can solve for pH, right? Because that's what I'm looking for is pH. And we do have a relationship that says pH plus POH equals 14, okay? And so I can utilize that and calculate pH, okay? And so I can take 14 minus 1.40, right? That's going to be pH, right? 14 minus POH gives me the pH. And so in this case, 14 minus 1.4, I guess I should do that in my head, but that's okay. That would be 12.60, okay? So I can do that, right? Because 14 is an exact value, guys. And then we have a 2 decimal place number, so I should have 2 decimal places after my subtraction. Or you could take this hydronium that we calculated and say that pH equals the negative log of the hydronium, right? And so that means the pH is the negative log of 2.5 times 10 to the negative 13th, okay? And so if you do that, 2.5 times 10 to the negative 13th, and I take the negative log of that, I also get 12.60 as my pH, okay? So no matter which route you end up taking, you're going to get the same answer. So this is 2 possibilities, guys. You wouldn't do both of those. You would either go the route on the left-hand side of the slide or on the right-hand side, okay? But I just want to show you that there's kind of 2 ways that you could go about this. And that's because those 4 things, pH, POH, H3O plus, and OH minus, they're all tied together. So once you know one, you can always get the other 3, okay? And so sometimes it leads to, you can actually solve for things in multiple ways. You can go one way or the other. Sometimes the pathways are, the same. Sometimes you choose the longer route or the shorter route, okay, whether you meant to or not. So let's see. Let's look at a couple more. I'll go a little bit quicker though. So here we go. We've got, what is the pH of a 0.116 molar solution of barium hydroxide? Okay, so again, you're given a concentration of some substance. So you're not directly told, how much hydronium or how much hydroxide, you're told the concentration of the substance, which is pretty typical. Okay, what you need to realize is that is a strong base. Okay, and so remember last time I gave you lists of strong acids and strong bases. You should utilize those lists, okay, and see if you have a substance that's on that list, then that means it ionizes completely. So in this case, you would have barium hydroxide. And when that ionizes, when it breaks apart, you get Ba2 plus, and you get 2 hydroxides, okay? And so you've got to be able to break that apart. And this is very important that you get 2 of those, okay? So that means if you started with 0.116 molar, you actually have twice as much of the hydroxides. You actually have let's see, if we take 2 times 100 or 0.116, we get 232 should be molar. Okay, so you have twice the concentration because for every one of those that breaks apart, you get 2 of those hydroxides. Okay, and so now I can use that to go and calculate pH, similar to the last one. Okay, and so I could calculate it in a couple of ways. I'm going to go the route of saying, okay, let's calculate pOH. pOH would be negative log of 0.232. Okay, and so if I take the negative log of that, and so 0.232, and hit the log button on my calculator, change the sign, and that has 3 sig figs, so I should have 3 decimals for my pOH, so that's 0.635 is my pOH. And then I can calculate my pH. My pH would be 14 minus that value, right? Because pH plus pOH should be 14. If I take 14 minus that pOH, that gives me my pH. And so that gives us, and we'll still have 3 decimals because the 14 is exact. That doesn't impact our sig figs. So 3.365. Okay, and so that would be my pH. Okay, and in this case, I haven't really been looking at those values on those last ones, but this is a strong base, right? I told you it's a strong base. So the pH should be very high, which it is, okay? If you got some pH that was less than 7 and you're dealing with a base, it can't be right, okay? And so if it's a base, it should have a pH greater than 7. If it's an acid, it should have a pH less than 7, okay? Now, let's look at one more example, and then we'll kind of talk about the final little piece of this chapter. So let's see. Oh, I have that. What's the concentration of HNO3 in a solution with a pH of 2? Okay, so this one seems like it's a totally different question than these others, but it's not. It's still tied to all of these calculations. So I give you the pH, right? I tell you it's 2.0. And I want to know what is the concentration of HNO3. Okay, what is the concentration of that to create this pH? Okay, so what you should think about is, okay, if I have pH, I know that pH is equal to the negative log of H3O plus, right? And so the more useful form of that equation would be the rearrangement. Okay, so I'll use the rearrangement that solves for H3O plus. So this is where you do the anti-log. You do the 10 to the, and we do the negative pH. Okay, and so I can utilize that and it'll tell me the hydronium ion concentration, which then I can relate to the actual concentration of the acid. So I'll do 10 to the negative 2.0, okay? And what is that? Well, I guess that, I don't even know. But yeah, 10 to the negative 2. We're just doing it straight to the negative 2, not to some crazy decimals. So I guess that makes sense. So we have H3O plus equals 0.01. And really I have 1 decimal in my pH, so I have 1 sig fig in my concentration. And so that's the molarity of H3O plus. Then what you have to realize is HNO3, that's a strong acid, okay? The strong acid, which those are, we only do quantifications for strong acids, strong bases, okay, guys? Weak acids and weak bases, it's a lot more complicated. That's why all of these I've given you are strong, okay? So if I'm asking you to do calculations and I give you a concentration of an acid or base, you should probably assume it's strong, because the weak ones, I would have to give you a lot more info, okay? Okay, so if I know that's a strong acid, that means when I put HNO3 in water, what I get is H3O plus and NO3 minus, and it completely breaks apart. That means that if I end up having a solution that's 0.01 molar of H3O plus, it must have come from a 0.01 molar solution of HNO3. Okay, that has to be where that came from. Okay, okay, guys, so you've got to be able to use those equations and convert between pHs and POHs and H3O plus concentrations and OH minus concentrations, and realize that those concentrations of hydronium and hydroxide directly relate to your strong acid or strong base concentrations, okay? If they're weak acids or weak bases, it's more complicated because you would have to tie in the Ka values or even AKB if you're talking about a weak base, but we're not doing those calculations, okay? But you should understand the basics of, if you have a weak acid or weak base, that they do ionize, but less than a strong acid or a strong base, okay? So you would have something less. If you had, say, a 1 molar concentration of a weak acid, you would have less than 1 molar of H3O plus, okay? Whereas if it's a strong acid, you would form all of that, so it would be 1 molar of H3O plus, okay? So just, try to remember the difference between strong and weak acids and bases. So the last part of this that we want to talk about is buffers. So buffers are an important thing if we're wanting to kind of regulate the pH of something, okay? So sometimes we have a scenario where something's happening in our system to create acid or create base, or for some reason we add some acid or base to something. And if there's additional acid or base, what happens is the pH can drastically change, okay? But if we need it to stay regular, so like in the human body, we need our pH to stay pretty constant. If it goes too high or too low, that can cause a lot of problems, okay? And so biological systems and sometimes reactions that we do in the lab won't work right if we don't keep the pH constant. And so what we do is we use what's called a buffer to help keep a pH constant. So a buffer is some sort of solution that actually can resist changes in pH, okay? And we can make them at any pH depending on what we start with. So normally you have a goal in mind. This system needs to be kept at a certain pH. So you would find, a system that can hold things at that pH, okay? It's going to depend on the actual substances, okay? Whereas how well it resists changes in pH is going to depend on how much of those substances are in that solution, okay? Now, what a buffer is made up of is either a weak acid and its conjugate base or a weak base and its conjugate acid. So you have a conjugate acid-base pair, okay? So that's what it is. If we have a weak acid and its conjugate base, or a weak base and its conjugate acid, that's a conjugate acid-base pair, all in the same solution. If you have that, then it will act as a buffer, Okay, so I give you some examples here. So like HCN is a weak acid and its conjugate base is CN minus. So that's when it loses a proton. Okay. Or for example, NH3 is a weak base and its conjugate acid is when it picks up a proton. So NH4 plus. If you have, one of those conjugate acid base pairs in solution, it can act as a buffer. It can regulate pH. Now, how it does that is by actually reacting with acid or base that is added, okay? And so the special thing about this is when you have a conjugate acid-base pair, that acid and base, they can't react with one another. So like when you have HCN and CN minus, even though HCN is an acid and CN minus is a base, they won't actually neutralize one another. Because if they did, they would just reform each other, okay? And so all they'd be doing is exchanging a proton and reforming what you already had, okay? So that's the trick with a buffer, is you create a solution that has an acid and it has a base, but they aren't capable of neutralizing one another. But they can neutralize other added acids and bases, okay? So what happens is the acid component of the buffer reacts with any OH minus that is produced by some added base, okay? So when we add a base, we're essentially increasing hydroxide, right? And that hydroxide will then react with the acid of the buffer. Whereas if you add acid, you're increasing hydronium in your solution, and that hydronium would react with the base of the buffer, okay? Now, in order for it to be an actual effective buffer, you do have to have a significant amount of both. So you can't have like a lot of HCN and very little CN minus. You need to have, pretty equal amounts or relatively similar amounts and quite a bit of both so that they can adequately neutralize added acids or bases, okay? So I do have an example there with that hydrocyanic acid and the cyanide buffer. And so when you have those two pieces, if you add OH minus, the OH minus reacts with the HCN, forming then that conjugate base, the CN minus, okay? So even though that reaction creates base, it creates part of that conjugate acid-base pair. And those things, when they're in solution together, have a specific pH, okay? And it stays relatively close to that, okay? Now I have some more examples of kind of how a buffer works, so how a carbonic acid buffer works, and how, buffers in the body work and acid rain. So if you want to look at some more examples, they're with the slides. Otherwise, that's basically it. We will do a lab, or let's see. No, your lab this week has to do with pH. I don't think I've got a buffer lab assigned for you guys. And so this is about it. But this is, with buffers, just realize, guys, this is a really useful thing in the lab, because a lot of times things can be very sensitive to pH changes. So it's useful to have a buffer. And so you just need to realize the basics of a buffer. What does a buffer do? What's its purpose? And how does it do that? And it does that because it contains both an acid and a base. So it can neutralize added acid and base. Okay. So that's it for chapter 13 then. So you've got homework that's due tonight if you haven't already done it. And then you'll have a quiz that you've got to get done by tomorrow. And then you've got the test that'll be posted Thursday. Okay. Watch for email. I think I may not have posted the study guide. I will look. If I haven't posted that, I'll get that posted today and email you guys. I might just go ahead and leave the test open through the weekend in case you guys want a couple extra days to study before you take it. So I'm okay with you guys taking it. If you don't take it by Friday night, like the original schedule would say, as long as you get the exam done by Sunday. If you want to do it on the weekend, feel free. I'll send an email letting you guys know, reminding you of that. Okay. Have a great rest of your week, guys. And I will see you Tuesday if you don't, log in for questions on Thursday. Okay. Have a good one, guys.